Absolutely, day one.
Let's do it.
Yes, it is empty. If I got a function f that's described as a function's output is x plus 3, then what does f send 2 to? What does f send 7 to? Do you think this is a one-to-one function?
Yes.
How do you know that?
Because it's a line.
It's a one-to-one function.
It's a line, it's non-horizontal, non-vertical, therefore it's a one-to-one function, satisfies a horizontal line test. It's a gimmick, it's not abiding by definition of one-to-oneness, but at least we can clarify visually that it's a one-to-one function. Since it's a one-to-one function, does it have an inverse? Yeah, I think it does. And I think its inverse function basically does this. It maps 5 back to 2, it maps 10 back to 7, it just simply takes all the elements in the range of the black function and transforms to all the elements, the corresponding elements in the domain of the black function. So when I got a one-to-one function, I've got a corresponding inverse function, I can reverse the arrows. You know, sometimes I like to think of a function this way. Here is an x squared, here is an e to the x, here's a natural log of x. What about a function that maps x squared to this? Or maps e to the x to this? Or maybe even maps the natural log of x to this? What kind of function is that? Say it again. Yeah, it sort of looks like a derivative function. Oh shoot, I can't say it that way in English, can I? I guess back in Math D, functions mapped numbers to numbers, and now all of a sudden I talk about a process that's mapping functions to functions. I guess I can't use the word function anymore. How about saying I got a differential operator? Let's see if my language is okay. What's f evaluated to?
5.
What's f evaluated to 7?
10.
And maybe over here I can say, well, this differential operator acting on x squared is, and maybe this differential operator acting on the natural log of x is
1 over x.
I think it operates sort of like the functions you and I had back in Math D. That being the case, jump back to Math D.
Did you conveniently choose this Math D reference just so you can say it's all Math D? Just keep saying
Absolutely, don't always. And so if I were to reverse the process, take the square root of 4 I get.
2.
I can't hear you. Take the square root of 4 I get.
plus or minus 2.
Ooh, yeah. When I reverse these arrows, I get choices. When I reverse this arrow, I get choices. Do you guys see my point? Maybe that function f is not really a one-to-one function. And so maybe there's more than one thing in the first set that gets mapped to the item in the second set. Actually, do you think I can redraw the picture in the middle board? What did I say gets mapped to 2x? What was that? Well, with the differential operator, what would happen if I had an x squared plus 3? What would that get mapped to?
2x.
And what about an x squared plus any constant c? What does it get mapped to?
2x.
So maybe when I undo the differentiation process, which is right after the break in 10 minutes, maybe it's going to be sort of like the squaring function back in Math D. Maybe in undoing the arrows, I might get more than one response. Do you guys see my point?
Yes.
You know, quite the contrary. I'm not going to restrict anything. I'm just saying, when I undo the differentiation process, I might get more than one function, whose derivative is what I started with.
Would we be getting infinitely many functions at that point?
Yeah, absolutely. I will indeed get a whole family of curves, a whole family of functions, which is an infinite collection of functions, because a constant could be anything you so choose. I agree. So everybody, it's time. We have spent the time this semester, all of our time, studying something called the differential calculus. It's now time to study a whole different branch of calculus called the integral calculus. Have I talked about Sir Isaac Newton and Leibniz?
Nope.
Really? Historically speaking, It is the case that we studied these two, what we thought were some completely different branches of calculus. We're finishing differential calculus? Well, not finishing. We studied the differential calculus, and now I'm going to start undoing the differential calculus, which involves the integral calculus. And what has happened, historically speaking, is that there was a horrible period of time in world history, particularly in Europe, called
Dark Age.
you know, you're right. The Dark Ages is where we didn't have the knowledge of the Greeks. The Moors stole it, hid it in Spain. But besides that, what great disease occurred?
Black Death.
Black
Yeah,
Plague.
the Black Plague. At which time Sir Isaac Newton was at Cambridge University in England. And with the Black Plague, everybody was sent home for years. And Sir Isaac Newton was in isolation. He did a lot of writing. But Sir Isaac Newton did not like to publish. And so he finally discovered this wonderful, wonderful connection between what we call the differential calculus and the integral calculus, which is what we're studying tonight, starting tonight. And he just didn't publish. And he was English. And of course, he communicated this to his colleagues at Cambridge whenever he came back after the Black Death subsided. But in Germany, a mathematician by the name of Leibniz, a little bit later, came up with the same discovery. But he published right away. And there was this enormous dispute whether or not the Germans ripped off the English or the English ripped off the Germans. And it was just a constant argument over this one issue for decades. Historically speaking, it took us a while, but we finally came to realize, with studying the results, studying the history, that both Newton and Leibniz came up with these notions independently. It's just that Newton came up with it first, but Leibniz published his issues first, or his findings first. And so, I'm finally going into the other branch of calculus, called the integral calculus. And I will even establish that bridge that joins the gap between the two, called the fundamental theorem of calculus. I'm just not going to do it tonight. We'll get there soon. Yes?
So you're saying this whole antiderivative process was born out of darkness and death?
No, actually, this undoing of the differential calculus was already established before Newton and Leibniz. I'm just saying they saw a connection between the two that we call the fundamental theorem of calculus.
But if it wasn't for the Black Plague, we probably
Would have kept the
taken
two
a long
calculi separated. That's why some people think of mathematicians as snobs. They say, oh, study the calculus. I mean, why do they use that definite article, the, in front of calculus? It's because we finally unified with Newton and Leibniz, these two different branches. And that's why we now call it the calculus, because now it's just one whole topic. Now, I'm not going to get to that wonderful theorem that both those mathematicians came up with tonight. When I do come up with it before this mess is over, I promise you I'll come to class and I will prove to you it's got to be true. For now, for tonight, I think I want to get started on just undoing the differentiation process. And that's what we're going to get to after the break.